Today is Friday. Ionic nomenclature, polyatomic ions and ionic compounds. There's a short handout that you can download or not. And then if you have an iPad and GoodNotes, there's a GoodNotes version that you can write on right here. All righty, so I'm gonna go ahead and get started. If you haven't watched the Zoom that talks about ionic compounds, I think it was Wednesday. Today's Friday, yeah, Wednesday. Then some of what we're doing might be a little confusing. And it's okay if you don't know and if you ask questions. And then for some of you that have watched Wednesday and Thursday and now you're here now, I'm going to be saying some of the same things over again. That's okay, because nomenclature is one of those things that just takes a lot of practice, reiteration. I know something is a compound if there's more than one capital. So this is a compound. This is not a compound. This is a compound. This is not a compound. So it has to be more than one capital, meaning more than one element, and no charge showing. And then if both those elements are not metals, then that is covalent. And we're going to learn how to name those next week. If it starts with a cation, which is usually a metal, and the metal would always be named first, so it would be metal and then non-metal. That's ionic, and that's what we're focusing on today, is ionic compounds. I want to say that there is one instance where you have the thing that comes first is a cation, but it's not a metal, and that is there's going to be this exception, and that is ammonium ion. Ammonium ion behaves as a group 1 metal ion. So it's a chunk of charge. It's a nitrogen and 4 hydrogens all stuck together covalently that have lost an electron and behave like an alkali metal ion, like sodium ion or potassium ion. And how it operates, for example, in water, which is something we'll look at later this semester. So if I were to see something like this, even though there are no metals there, I would have to recognize, if I break it apart, I recognize ammonium. This is ammonium chloride. In our class, ammonium is the only cation that is not a metal ion. Okay, so we're looking at polyatomic compounds, ionic compounds that contain polyatomic ions. And polyatomic just means many atom ions, like ammonium is our one polyatomic cation. But there are lots of polyatomic anions. Cyanide, maybe you've heard of that. Hydroxide. And then there's going to be a whole bunch that end in ate and ite, like nitrate and nitrite. And so some of these you're going to need to memorize, and some of these you will, once you understand a rule and a pattern, you'll be able to deduce. And that's what we're going to talk about a little bit today. Where can you find all of these? You can find these in the nomenclature packet. So let me go to the module that is this week, week 5. To the page we're talking about, ions and ionic compounds. On that page is a 33-page packet, but don't be alarmed. Some of the pages have all the answers, so that's always good, right? And so here's what we talked about Wednesday, and we practiced putting things together and naming them. And then, so this practice we didn't do. We did something similar to it, but you can do this practice and then check your answers. And then we talked about transition metals and how you have to state the charge. We have some practice for that, and here's a key. And then it's important that you do building ionic compounds exercise with variable charge and fixed charge. because now you have to decide, do I state the charge on the cation? Is it a cation that has more than one charge choice, or do I not state the charge? And this is something that we did Wednesday. So here's cesium. Cesium is a group 1 metal. When it forms an ion, the only choice is +1. So I would just say cesium for the answer of in this box. I would just say cesium chloride. But here's cobalt, and cobalt does have charge choices. It's a transition metal. So I would need to say, for the answer for this box, cobalt-3 chloride. And then sometimes we have exceptions, like tin isn't in the transition metal area, but it does have charge choice possibilities. So I have to say tin-4 chloride in that box. So we talked about that Wednesday. And then there's the key. There is some common nomenclature for some transition metals that only have 2 charge choices. Okay, now this is the polyatomic ions that I want to focus on today. Wednesday, I covered all those first pages, and then Thursday we practice. But today, Friday, I'm going to talk about these. And so, oh my gosh, this cat is so annoying. Okay, so you need to memorize these, and there's 4 of these that are super important, and they are the first 4. They're the chlorate, sulfate, phosphate, and carbonate, because they are anchors. They tell us what the rest of the elements in their group are going to do. And then there's some other ones you need to memorize. You may be thinking, well, do I really need to memorize these? Because, you know, I'll have this list next to me when I take a test. And the answer is, it will make your life easier if you just learn them. So I recommend that you just learn them. And then there's a grid that puts it all together. So now we have all the possibilities that we've learned so far. You need to do that one. And then I want to talk about derivatives, and that's other 8s. And that's how far we're going to get today. We're still going to put things together, cations and anions, in a way that they add to 0. And if our anion is polyatomic, or a cation, the only polyatomic cation is ammonium, and there's more than one, we use parentheses. So here I have calcium ion. I look on my periodic table, I find calcium. Calcium is in group 2. Metals in group 2 lose 2 electrons to be isoelectronic with the previous noble gas. So calcium's formula, calcium ion, is that. Then nitrate is just something you have to memorize, NO3 minus 1. Because I need 2 nitrates to balance that calcium plus 2 charge, I'm going to need parentheses. So calcium, and then I put parentheses to say 2 of these, 1, 2, nitrate. When we put things together in ionic compounds, even though the ions still have charges, we don't show the charges. And if we showed the charges, it would be wrong. So if I were to write it like this, that would be wrong. And then the reason we need parentheses is if we don't have if we don't have parentheses, we're not representing things correctly. Do we really mean 1 calcium, 1 nitrogen, and 32 oxygens? No. Now, once people learn about parentheses and get all excited about it, they might look at something like calcium chloride. And so here's calcium and here's chloride. And I'm going to need 2 chlorides to have the charges add to 0. This is correct. This is not. Even though chloride has 2 letters, there's only 1 capital. There's only 1 kind of atom there. So adding parentheses would be wrong. Okay, ammonium is NH4+. It is our 1 polyatomic cation. Just pretend that ammonium has a spot here with the alkali metals. It's like the adopted alkali metal ion. It's part of the family now, and it behaves in the same manner. So ammonium is a +1. Nitrate is a -1. They come together in a 1-to-1 ratio. I know that's a lot of capitals all stuck together, but that's the correct formula. And then later when we have to name things, we just have to recognize that chunk of charge, which is ammonium. That's one of the reasons it's a good idea to memorize those. Okay, iron 3. Most cations are monatomic. The only one in our class that isn't is ammonium. And nitrate, we're going to need 3 nitrates. So 4 ions are all adding together, and iron 3, a nitrate, a nitrate, a nitrate, plus 3 for the cation charge, minus 3 for the anion charge. The reason that I highlight that is we're going to have to be able to construct ionic compounds, and then when we put them in water, many times they deconstruct and they break into the ions that they're made of. And we have to recognize that iron 3 nitrate was made from 4 ions, and so it breaks into 4 ions. It doesn't go into water and suddenly become, you know, nitrogens and oxygens floating around. Okay. Hydroxide. It's a little odd that it ends in "ide." Typically, when we see that "ide" ending, we're thinking that a nonmetal has gained enough electrons to be isoelectronic with a noble gas. So if nitrogen gains 3 electrons to be isoelectronic with neon, we call it nitride. If sulfide is isoelectronic with argon, because it's gained 2 electrons and now it has 18, and then bromide can gain 1. So there's a bunch of nonmetals that can gain electrons to be stable. And when they do that, they end up with an "ide" ending. So it's a little strange that hydroxide has an "ide" ending, but it does. The next thing is, it is a polyatomic, and it does need parentheses if there's more than one, even though, even though it doesn't look very poly, it looks sort of diatomic. Okay, so hydroxide is OH minus 1. Calcium hydroxide, we're going to need 2 hydroxides. Ammonium hydroxide comes together in a 1-to-1 ratio. Iron 3 needs 3 hydroxides because the charge on hydroxide is minus 1. Okay, and then here we have sulfide, and sulfide is just one of those ides. Sulfur has gained 2 electrons to become more stable. Calcium is a +2, sulfide is a -2. So this is like what we were doing yesterday. Ammonium is a +1, sulfide is a -2, so we're going to need 2 ammoniums. And then we have iron 3 and sulfide. The lowest common multiple is 6. I'll need 2 iron 3s to go with 3 sulfides so that the unit for the formula adds to 0. Okay, so forming compounds is one thing, and then naming compounds is another. To name these compounds, I need to break things apart from cations into cations and anions. And so I look at this, and I recognize that the cation is going to be on the left, just like the metal is on the left on the periodic table. And so sodium is an element I recognize, and sodium is in group 1. So everything else over here is a polyatomic that has a -1 charge because they came together in a 1-to-1 ratio. This is sodium, acetate. So acetate is one you're going to have to memorize. A student once showed me this, and I thought it was very clever. Acetate is C2H3O2 -1. And sodium acetate, the word, looks a little bit like nacho. And who doesn't like just a huge plate full of nachos? Yum. big heaping plate. And so this is how they remember 232 is by the shape of the large plate of nachos. And then CHO means CHO. And we know sodium is a +1, so acetate must be a -1. I don't know if that helps.
No, I got it now.
I thought it was very clever. Thank you, Sunny.
Yeah, no, that'll help me for sure.
I love nachos. Yum. Okay, so here I have 3 capitals, and I have to decide how to break it apart. Well, the metal comes first. Do I recognize that metal? Sure, that's silver. So I have 2 silver ions, and silver ion can only be +1, even though it's a transition metal. There's only one charge choice possibility. And then CO32- is one of the anchors that I need to memorize, and that's carbonate. This is silver carbonate. Break it apart. Oh, I recognize acetate, and there's 2 of them. So this must be, there's 1 cobalt and 2 acetates. And acetate is -1, so this cobalt must be +2. Cobalt 2, acetate. So it's not enough that I know acetate is C2H3O2. I have to also know the charge, because if it's with a transition metal, we have to deduce what the charge on that transition metal is. Here's cobalt. Cobalt has 2 charge possibilities. It can be +2 or +3. There are 3 that are like that. And so I have to say which cobalt is in the compound. And in this case, it was cobalt 2 acetate. If it had been cobalt 3 acetate, the formula would have been like this. But because of this 2, I can figure out what the charge is here. And that's what this is. It's us stating that charge. Okay, ionic compound. I know it's a compound because there's more than 1 capital, no charge showing. I recognize it's zinc is a metal. That's how I know it's ionic. Zinc is here on the periodic table, and silver, zinc, cadmium, and then these are group 3. They form sort of this stair step of +1, +2, +3 fixed charges. So I know the charge on zinc is +2. It's always +2 if it's an ion. So I don't state the charge, I just write zinc. Because it has a fixed charge, we don't state it. And then PO43- is an anchor you're going to memorize called phosphate. This is zinc phosphate. Compound, there's more than 1 capital. Ionic compound, because that's a metal. Lead is one of the ones that has charge possibilities. Tin and lead can be +2 and +4. So I need to know which one I'm working with. Sulfate is one of the anchors you're going to memorize, and it is a -2. And because they came together in a 1-to-1 ratio, this must be lead 2. Sulfate. Okay, this is a compound. 1, 2, 3, 4 capitals, no charge showing. Even though it's all nonmetals, I recognize ammonium, and so I know it's an ionic compound. There's 2 ammoniums and 1 sulfate. This is ammonium sulfate. Now I'm going to talk about derivatives. You don't have to memorize every ion. You can just memorize the ones that were on the list. And there's 4 that are especially important. So, and the 4 that we're talking about are nitrate, sulfate, carbonate, chlorate, and phosphate. And I'm going to give you a mnemonic to remember those that may or may not help, but here we go. Nick, the camel. 8, a clam. For supper. in Phoenix. So there are 5 nouns in this sentence. Nick, camel, clam, supper, and Phoenix. And each noun stands for one of the polyatomics. And every consonant is an oxygen. And every vowel is an extra electron. And so Nick stands for nitrate. There are 1, 2, 3 consonants, 3 oxygens. There's 1 vowel, 1 extra electron. That's why it has a -1 charge. Camel stands for carbonate. Carbonate is carbon with some oxygens and extra electrons. How many oxygens? 1, 2, 3 consonants. How many extra electrons? 1, 2 vowels. That's carbonate. So these are all 8s, and 8s are nonmetals combined with oxygen that make anions, negatively charged ions. Clam stands for chlorate. Chlorate is chlorine plus some oxygens. How many oxygens? 3. How many extra electrons? 1. Supper stands for sulfate. And Phoenix stands for phosphate. So sulfate is sulfur with some oxygens. How many oxygens? 1, 2, 3, 4 consonants. And extra electrons, 2. Phoenix stands for phosphate. Phosphorus gains oxygens, 1, 2, 3, 4, and has 3 extra electrons. So why are these so important? And the answer is, Nick's not that important. The other 4 are the line leaders. So for the nonmetals that gain extra oxygens, we have carbonate. If we know the formula for carbonate, it tells us silicate and germinate. Same number of oxygens, same extra electrons. And then clam is for chlorine. And if we know chlorine, we know chlorate, bromate, iodate. It tells us what's happening in that column. Camel, oh, we did that one. Camel was carbonate. Supper is sulfate. Sulfate is the line leader. It tells us what selenate and tellurate would also be like. And then Phoenix. And if we know phosphate, we know arsenate. That may seem like a lot of work just to get a couple extra polyatomic ions out, but there's more to it. Let me go ahead and clear some space and show you what I mean by that. So if I know carbonate has 3 oxygens and 2 extra electrons, and I was asked about silicate, 8s in the same column behave in the same manner because columns are families. They behave in a chemically similar manner because they have the same number of valence or outer shell electrons. So however carbon behaves, non-metal below it, silicon, is also going to behave in that manner. And so silicate will also have 3 oxygens and 2 extra electrons. So there's metals and nonmetals, and then there's the semi-metals, things that are touching this line. Turns out semi-metals and metalloids often behave more like nonmetals than metals. And so germanate is like carbonate and silicate. Germanium, which is below carbon in the same family, group 4, would also have 3 oxygens and 2 extra electrons. So if you know carbonate and you have a periodic table, you also know silicate and germanate without memorizing them. So here's phosphorus. Nitrogen is not the line leader. Phosphorus has the pattern. Phosphate is PO4 3-. Arsenate is ASO4 3- as well. Things in the family behave the same way. The phosphorus needs 4 oxygens and 3 extra electrons to be very stable. So does arsenic. Okay, here's sulfur. Sulfur has a very stable oxyanion, oxygen-containing anion, that's called an 8. Selenium and tellurium are below it, and so when they form 8, selenate, tellurate, same number of oxygens, same charge. The one that we are probably the most interested in is chlorine, because chlorides and chlorates are halogens and the 8s they make are super important. So here's chlorine, the line leader, not fluorine. Chlorine makes chlorate, 3 oxygens, 1 extra electron. Below chlorine is bromine and iodine. Bromate and iodate behave in the same way. I do know that if people take Chem 3A, it's possible they've never had chemistry before. This class is totally appropriate for people with no chemistry background, which is why I need to know from them if it's making sense. I don't want to waste your time by just talking gibberish. Okay, so we've talked about 8s. What is an 8? An 8 is an oxygen-containing anion, so a nonmetal with some oxygens and extra electrons. That is very stable. But ites are also possible. Ites aren't as stable as 8s, but they do exist. And the rule for finding an ite is take the 8 and make it 1 oxygen fewer. So now I want to talk about ites. We're familiar with nitrate. If we take the same number of extra electrons, but just 1 oxygen fewer, we have an ite. And that rule applies to every 8. Theoretically, every one of these has an ite. Now, in reality, they don't all have ites. But if you're asked in a Chem 1A class or Chem 1B class, what is chlorite? You know how to figure that out. It's like chlorate, but 1 oxygen fewer. So we have 2 rules now. The first rule was Nick the Camelot clam for supper tells us what the line leaders are. We have to memorize those, but they apply to everything in the same column. And then the second rule is you can make an ite from an 8 by removing 1 oxygen. And the third rule is going to be you can have a hydrogen-containing compound, a hydrogen-containing ion, and this is how we name them. We don't have to memorize them because we can derive them. So if I know carbonate, and I want to make a hydrogen-containing ion, so an ion still has a charge showing. Because it has a -2 charge, I can add 1 hydrogen ion and when I combine them, I end up with something that is still an ion, and this is called hydrogen carbonate. So it's kind of like 2 last names that aren't hyphenated. If I had sodium hydrogen carbonate, there's 1 cation and 1 anion, and it's called sodium space hydrogen space carbonate. Like Catherine Zeta-Jones. But hydrogen carbonate is one ion that sticks together in a polyatomic chunk. Unfortunately, before we made a systematic way of naming things, people were already naming things, and sodium hydrogen carbonate is really common. The other way to name it is to call it bicarbonate, which is one word. So this is also known as sodium bicarbonate, and you probably have it in your kitchen. That's not IUPAC, the International Union of Pure and Applied Chemists, systematic way of naming, but it is real, and you're going to run into it. So if you have a hydrogen-containing oxyanion, that's a mouthful. It can also be called a bi-something. So there's phosphate, and if you add one hydrogen ion, it's biphosphate or hydrogen phosphate, and those are synonymous. Let's do it a couple more times. So here I have phosphate. And I can add a hydrogen. And when I do that, the charge changes by 1. It goes up by 1. So what was -3 is now -2. And that is called hydrogen phosphate. But it can also be known as biphosphate. But wait, we can do that again, because -2, we could add a second hydrogen to it. So now I'm going to take hydrogen ion plus hydrogen phosphate. And when I combine them, I now have 2 hydrogens of phosphorus and 4 oxygens, and the charge goes up by 1. This is called dihydrogen phosphate, and it is the only name for that one. It's not like bye-bye phosphate or anything like that. Let's see if we can do that a third time. If I was to add a hydrogen ion to a dihydrogen phosphate, what would I have? Oh, I don't have an ion anymore. This is not trihydrogen phosphate. It's not an ion, and this rule of adding hydrogens to make hydrogenates only works for ions. It's a compound. It's a covalent compound that is named as an acid, and the only correct name for this is phosphoric acid, which we'll deal with next week. The only reason I mention it now is I want you to be clear that we can do this trick of adding hydrogens as long as we end up with an ion. And then we just add the word hydrogen. What is this? It's an ion, a chunk of nonmetal stuck together with an extra electron.
Hydrogen sulfate.
Close. This is hydrogen sulfate.
Dang it.
No, it was tricky, Melissa. Thank you for taking the bait. So what is the one on top?
Hydrogen sulfide.
Good. Yeah, so we can apply more than one of these derivative rules to come up with something. Okay, good job. Now that you know the trick, let's do it again. So you can apply more than one derivative rule to come up with the correct name. And if you don't know where to start with, well, I know it contains oxygen, so it's an 8 or an ite. And bromine is in group 7. Who's the line leader in group 7?
Chlorine.
Chlorine. So what is the formula for the 8 that you know? Chlorate. Okay, so if we went down the column, we could write bromate, because we know chlorate. And if what we have is one oxygen fewer, isn't that an ite?
I have a very dumb question to ask. Why wouldn't we say it like bromine oxide or something?
Because nonmetals, so the first one is always a nonmetal, and then it's grouped with some oxygens in a way that it makes a chunk. And we haven't learned how to make these yet, but like chlorate looks like this. It's called a Lewis structure. And so that covalent chunk of charge is an 8. Whenever we have a nonmetal with oxygens, that and extra electrons, that's going to make something called an oxyanion. And oxyanions end in ite or 8. And the one that is given the 8 ending is the one that is more stable. And so the ites typically air oxidize to become 8s. They change into 8s. They exist, but they're not very stable. So I don't know if that even, Michelle, did that even address your question?
Yes. Thank you.
So here's something I learned during the summer. When people take things online, some people have give in to their moral weakness and they cheat. I mean, we all struggle with our ethics, but when people cheat, they'll look up answers, and not every answer in chemistry online is correct. And so I will typically ask something like this, and I see something like bromine trioxide iodine or ion. And so I'll see the same weird. In the summer, I saw some wrong names I've never seen before, and I've been teaching this 20 years consistently. I thought, whoa, they're either sharing answers or looking at the same site, and it's wrong. So I don't get to make the rules. I just learn the rules and share the rules. And those are 8s and ites. But to help you understand it, just understand there's a nonmetal with oxygens. That's going to be an 8 or an ite. Now, you ready for the 4th rule? Group 7 is funny. Group 7 does things a little more extreme. So what is group 7?
Running out of paper over here, Sue.
Okay, I promise it's the last one. So I'm really talking about chlorine, bromine, and iodine, because fluorine is super reactive and does its own thing. It just rips electrons off of everything. So I'm really talking about chlorine, bromine, and iodine. Let me start with chlorate. And then everything I'm saying here works for bromate and iodate in exactly the same manner. So we memorize this one, chlorate. It's our anchor for group 7. And then we know one oxygen fewer would make an ite. But for the group 7, there are more possibilities. There is an oxygen-containing anion, an oxyanion, that has 4 oxygens, and an oxyanion that only has 1. And so the 8 and the ite still works. This one is going to be related to chlorate, and this one is going to be related to chlorite. But we needed another word. And so prefixes are added. The prefix that means under is hypo. A hypodermic needle goes under the skin, under the derm. So under the ite is the hypoite. Hypochlorite is that oxygen-containing anion. And if you look on your bleach bottle, you probably have hypochlorite in your somewhere in your house. So it's a real thing, and we need to identify it and name it. And then more than could be hyper, but we don't say hyper, we say per. More than the 8 is the per8. So perchlorate is an oxygen more than chlorate.
This is only for group 7, right? So you
Yes.
said,
That's right. Go ahead and give me the formula for calcium hydrogen sulfate. Okay, I'm not seeing any raised hands, so it makes me wonder what's happening out there. Away from keyboard.
I'm here.
Scared.
So I'm trying to show my thinking. The first thing is, you know, find the cation on the periodic table and what's its charge. And the transition metal one, I had to tell you what the charge was, iron 3. And then here, it's not sulfate, but it's related to sulfate. So I start with sulfate, and then I add the hydrogen, and I see how the charge changes. So that's me showing my thinking. I don't know bromite, but bromine is in the same column of chlorine, and I know chlorate. So I start at chlorate. My anchor is a good starting place. And then germinate, I know it's an 8. Let me find something that looks like German on my periodic table. And then what column is it in to find my line leader, carbonate. Okay, and then once I've done that, I can put it together. This is a +2 and a -1. I'm going to need 2 of those -1s. This is a +3 and a -1. I'm going to need 3 of those bromites. Sodium is +1, germanate is -2. I'm going to need 2 sodiums. And I don't put it in parentheses because even though sodium has 2 letters, it only has 1 capital. Okay, how do you feel? Today I will post, like I did yesterday, a list of, you know, here's 10 formulas, give me the name, here's 10 names, give me the formula. This time I'll put the derivatives in there. And then you can either come at 5 and work through those with us. It'd be better to try them on your own and then see them work through, or you can just check out the Zoom. Or you can do, you don't have to do anything, obviously. You're free agents, you do what you want. But let me just, again, admonish you that nomenclature just takes practice. Yeah. Okay, that's all I got.